Okay, so when you're working in a notebook on any particular workflow, whether it's doing some sort of mathematical operation or data analysis or whatever other sort of thing you might do, there's any number of things you might do. It's pretty typical not to be working with just one input and one output. So you need some sort of structure for your data and the calculations that you're doing on it. In Wolfram language, this structure is called the list, and it's represented with curly braces. So for an example, this is a list. It's just some things collected, separated by commas, with curly braces around them. Now, I will note that internally a list is represented like this, and if you were to type explicitly list, it will render like this in the front end. But typically, you just use the curly braces to type things. So you can just make your list like this, where you would type 1, 2, 3, 4, 5, whatever you want to type. And if you press enter, you can see here that this returns exactly what we put in without any issues. It doesn't produce an error or anything. A list can stand on its own just fine in a computation. Many different functions will take lists as their inputs. For example, this function called random sample will take a list and randomly sample it. Or if you provide some second argument here, we can get 3 random things from this list. The point is really that the list can serve as an input to a function just fine. Here is reversing a sort. We have a range here, which will take a sequence, and this one is going to output a list. This doesn't take in a list, as you can see here. This is there's no curly braces, so this isn't a list. This is a sequence in technical terms, but we could just say that range from 2 to 20 in steps of 3 produces an output, which is a list here. So 2, 5, 8, 11, 14, 17, 20, the numbers 2 through 20 in steps of 3, which is the step size between these. So all these lists we've seen so far have only one level. They are not nested, right? They just exist kind of as they are. But lists can be nested. They can have more than one level. So here's a list where each of the elements is itself a list, right? So we have a list where the first element is the list 1, 2, 3. The second is the list 4, 5, 6. And the third is the list 7, 8, 9. So that's a perfectly fine nested list. And again, if I were to just evaluate this as an input, it just produces the same output. It doesn't do anything new or novel or particularly interesting. It's just to note that this is a totally valid thing that you can write in Wolfram language. There are many functions that work with nested lists or produce multiple lists, or produce nested lists, rather. Matrix form is a function that you can use on a nested list in order to maybe visualize it a bit better. So this is kind of the standard way you'd write a nested list in Wolfram language, but maybe that represents to you a matrix, right? And so if you type matrix form and you just wrap your nested list in matrix form, you can visualize it as a matrix. And same thing here, random integer from 0 to 9, generate me a 4 by 4 matrix is what this means. We can do that. And if you wanted to view this as a matrix, you could. Note here, this is if you're totally new to Wolfram language, this may be a sort of surprising thing, at least if you haven't used a notebook interface before, that when I generate this output cell, I can just click right in it and start typing and use it as part of a new input cell. So there's my matrix form. There's a note about nested lists is that lists can be arbitrarily deep. There's no particular limit as to what the dimensions could be. So here is my list with random integer from 0 to 9, and it's going to be a 5 by 4 by 3 by 2 nested list. Kind of a mess, right? Matrix form will help us to make some sense of it. We can see that it's basically a matrix of matrices. It's a 5 by 4 matrix where each element is itself a 3 by 2 matrix. So as we can see, it's got 5 rows. It's got 4 columns. Whoops. And then each of the entries in that 5 by 4 matrix is itself a 3 row by 2 column matrix. And there's a question about this. You can name this any symbol you want, you know, happy birthday. Doesn't really matter what you name it. It's just a symbol name. It produces a list regardless of what you call it, you know. Definitely not a list, but it's still a list, you know. And there's also a request for me to upload the kind of completed versions of the notebooks where after I've gone through it for the day and it's, you know, everything's run and filled out and maybe I've added extra examples and stuff, I could upload that. Yes, I will try to remember to save the finalized versions, so to speak, and also drop those off in the uploads folder, in the materials folder, so that you have access to the recordings and the versions of the notebooks where I have typed some extra stuff. So again, if we have this, definitely not a list, even though again, it is a list. If we provide it to dimensions here, dimensions will tell us precisely the dimensions that we originally had fed into random integer, that it's a 5x4 by 3x2 nested list or nested matrix, however you'd like to think about it. And just a note for, you know, there are reasons that you might do this, although it's pretty rare. Lists don't even have a requirement on them that they need to be rectangular. Like all these things are rectangular, right? They have a certain number of rows and a certain number of columns, and then even the subparts have a certain number of entries, and it's all rectangular. So this is a rectangle, right? And then this is a rectangle. But lists don't need to be rectangular. They can be ragged or jagged. You might see both names in you know, the literature, so to speak, a ragged or jagged array. It's perfectly acceptable. So here, if I have this list where the first element is just a number and the second element is a list, and then the third element is this nasty nested list, and then the last element is itself just a number again, that's totally fine. And you can't really use matrix form on this because it doesn't look like a rectangle. You know, if you use column on this, it just produces this output here. It's not a particularly nice looking thing, but it's a totally valid thing. So something I can point out is, suppose I rename this and I call this definitely not a list 2. It's going to be a new version. Watch the left-hand side here when I press Shift Enter to evaluate it. This now says in 85. And if I were to do definitely not a list 3, watch the left-hand side again, in 86. So there's a history of all these things that we have run all throughout. And what happens each time you run a new line of code is, you know, that code runs by itself. It will use anything you've done before, right? But it's not going to overwrite anything you've done before just because it exists in the same place. There's nothing special about this line being right here that would make it overwrite its old definition. Any old definitions will just stick around unless you explicitly were to overwrite them by typing something like, well, now list is equal to this new set of random integers, or now happy birthday is equal to this new set of integers. But as you can see, if I look at list and happy birthday and definitely not a list, and you can also see them auto-completing here, suggesting they still exist. These things all still exist. Kind of a scary way to look at them, but they all do still exist as their own matrices here. Another thing that we will touch on is that whenever something is defined in Wolfram language, the symbol name turns black. So notice that matrix form is black. Definitely not a list is black. Happy birthday is black. These are all things that have some sort of definition associated with them. But if I type, let's type a different symbol name, unhappy birthday, notice that it's blue, right? This means that it doesn't have a value. If I run it, there's just nothing really there. But if I go in here and I were to say, you know, define it as a string, watch the color of unhappy birthday. Once I evaluate this line of code, it turns black. Now this is the thing that has a definition, so it is black. It doesn't matter whether you have given it a definition or it's a system variable that has a definition, or even if it's something that you've pulled in from a package. Pretty rare to use packages in Wolfram language because everything is built in. But even if you were to pull in something from a package, it would have a black coloring if it were a defined symbol. Now, the way you access the parts of a list is that you use the function part, right? So we could take this list and we could say, okay, part of the list, and give me the second part. And in that case, this would be a 4. But it's a little bit annoying to always be typing part. So the shorthand is that you use 2 square brackets and they will autocomplete and pretty print. So please don't be confused by that. If I just type one set of square brackets, I just type say a left opening bracket. Notice that it autocompletes as if this is a function. And if I type it again, it pretty prints the kind of version here that you see. So, well, the point was there to get a closer look at the pretty printing, but that broke the pretty printing by changing the magnification. So it just looks like that. Again, just type opening square bracket twice, and then you can extract any parts you like, the second part, the first part, the fourth part, and so on. And if you have a nested list, a list with more than one level, if you use only one index, it's only going to extract the parts at the top level. So here we have this nested list, right? And if we ask for the first part, it's just going to give us the first part, which is 4540. Now, if you had 4540 on its own and you wanted to access the second part of this, you would just do this. But of course, you don't want to have to, run multiple lines of code just to extract some nested element. So the way you do that is you just kind of combine these two ideas and you say, okay, go to the first part and then go to the second part of the first part. So here, this will just give us 5 directly. So we say, okay, go to the first part and go to the second part of the first part. So if we consider this nested 4-level list from earlier, the original LST, we could go to its third entry, get the second entry of that entry, the first entry of that entry, and finally the second entry of that entry, like this. So let's see what that means exactly. We're going to go to the third entry in the list. That's this. We're going to get the second entry of that entry. That's this. We're going to get the first entry of that entry, which is this. And finally, the second entry of that entry, which is that. And if we run this, we get the 9 that we just selected out there. And it's also worth noting a couple of tips and tricks for part. Say we have this list here, just a list of integers from 1 to 8. You can count starting from the back or index from the end by using negative indices. So you could get the second from the last element by typing -2 in your part specification. So the last element is 8, and then the second from the last would be 7. So that should give us a 7. And indeed it does. If you'd like to extract a span of elements, you can use 2 semicolons. So 2 through 4 is how you should read this. It's the span of elements 2 through 4. So that's going to be 2, 3, and 4. And if you need to extract just some particular disparate elements from a list, you can do that by providing a list of things that you would like to extract. So you can say, I want the fourth part and the last part and the second part and the third part. And there they are. Not particularly novel there to just be able to be like, well, I want the fourth part of a list that goes from 1 to 4 and you get 4. But say you need to get not some contiguous span of entries, but just some, particular entries that you're picking out for whatever reason. Maybe these are the positions where a certain thing appears that you're trying to extract. You can just put these elements or these indices in a list to extract the corresponding elements. And so far, we've just used integers as the elements of our lists, but that's not necessary either. Any type of element can be used in a list. So here's a function just like the random integer we used before. This is random real. So this will give us a random real between 0 and 1, and it will give us 20 different ones. And just like the one above, if I wanted to get a nested list, I could do, say, give me a 3 by 3 list of random real numbers. And again, this would work just fine in matrix form. So a list could have a bunch of reals. It could have a bunch of strings. Like if we go in here, we see that we have all these strings that make up the alphabet. The characters used in strings, they don't have to be from the Latin alphabet either. So you can have Greek strings, Greek symbols. You can also have Cyrillic. You can have all sorts of different alphabets. And if you look at the documentation for alphabet, you'd see which ones are possible. Lists can also have graphics in them, right? They don't need to just be, kind of simple in a sense. They don't need to be integers or real numbers or strings. They can be full, more complicated Wolfram language expressions. So I'll even make it a little more complicated here. Let's add some dark rainbow coloring. And so this is a perfectly valid list, even though each of these things is a real and, sufficiently complicated graphics object, right? They exist, all these graphics objects exist between these two curly braces, which are being cleverly and nicely highlighted for us because we are clicked, we're focused on elements in the list. We can see that they exist as a list here. And something I want to be really clear about is that these graphics objects aren't like thumbnails or anything. These are the real full graphics objects, the exact same ones you would get if you weren't making a list. So this thing and this thing are totally equivalent. Being in a list doesn't diminish it or compress it or do anything like that in any way. It is really the real element there. And, you can kind of indicate to yourself that this really is a list because it works like a list in all contexts. So say I have my list of graphics objects here. I could get the second through the fourth elements of that list by doing that. This is 2, 3, and 4. I could get the last element by doing that. I could get the first and the last element by doing that. It's just a list. The elements of the list are just a little more complicated in that they are full graphics expressions instead of just single things like strings or reals or ints. You can also use integers. So if I define cat to be this is an image, right? I could make a list using, say, table, where I binarize cat to different levels b, as b goes from 0 to 1 in steps of 0.1. And there we go. And I'm going to add a little image resize here so it fits a little bit nicer. Let's resize it to, say, 150 pixels wide, maybe. And maybe a little smaller. So there's the list. And these are all, again, real images that, well, they would be full resolution aside from the resize, but here they've been resized to be 120 pixels wide. But these are real, proper full images. There's nothing, again, there's nothing compressed or smaller or anything wrong with these things in any way. They are real, proper images that exist in a real, proper list. And notice that when I did this, I didn't have to type the list. That's not type as in, not that kind of type, but I didn't have to say, this is a list of images. Watch out, I'm going to fill it with images. I didn't have to say, this is a list of graphics objects. I'm going to fill this thing up with graphics objects, so it's going to have a length whatever. I just said, hey, give me a table of this expression as k goes from 1 to 5. And that expression produces a graphics object. So the resultant list is full of graphics objects. There's no explicit typing that we need to do. It's just that this generates graphics, and so the list has graphics in it. This generates images, and so the list has images in it. Suppose we have this here. Colors can also be part of a list. Just a note on the way these things are represented internally. Suppose I have 10 random colors. Here they are, all on a list. You can, again, treat these however you like. Get the second through the fifth random colors from this list. There they are. And just a note here, suppose I have this lovely looking 3D graphics object of a shape you've certainly never seen before. Definitely has nothing to do with the company. Just a note that a list can contain any combination of element types as well. So we could have just this undefined symbol A, an undefined symbol F, acting as a function on an undefined symbol X, an integer 42, a real 3.14, a color red, a string, a mathematical expression, a 3D graphics object. And again, we could add a 2D graphics object. Why not? Let's do sync of x as x goes from 0. Well, let's do negative pi to pi. And then let's do 2 pi. And again, we'll add my color function that I very much like, dark rainbow. And then we'll also put Meech in there for good measure. And if I evaluate this, we see that this is a perfectly valid list. No error messages or anything are produced about, this, you can't have all those different types of things in the list. It's just totally happy to do it. It's not a problem. Let's also make that sync a little bit nicer. Huh? There we go. We can see some more wiggles now. And again, every single element here is a real, fully functional element of whatever type it is. So this is a real 3D graphics object that can rotate. It's not like a screenshot of it that I've just inserted in here that I can't actually interact with or something like that. It is the real 3D graphics object. And this is a real image that I could then, say copy out, and I could do an edge detect. Scary. And here are just some more examples of lists here. You can partition a list into sub pieces if you like. You can extract all the elements here. This is a little bit redundant, because if you just type my list, you get it. But it's just a note to say that if you want to get all the parts at a particular level, you can type all and you'll get all those parts. And we'll show exactly why that matters in just a second. So suppose I have this horrible list, which is a 6 by 6 by 2 by 2. We'll again look at it as a matrix form. It's a 6 by 6 matrix where each element in the matrix is a 2 by 2 matrix. We'll cut that for now. But let's look here briefly at all the elements and then get the last element of each one. And then let's see here. Notice where these things are coming from. 8, 2, 3, 2. If you look up here, 8, 2, 3, 2. And then 2, 5, 2, 2. So what we've done by going all -1 is we've gone to all of the rows and grabbed the last entry. In other words, you can kind of think of this as grabbing the last column. It's rectangular, so you can think about it in terms of rows and columns if you like. Similarly, if I were to go here and I were to type 2, you can see that I get these. If I do use matrix form on this, what does that look like? It's a little bit confusing because of the structure. If I do this, I get the individual matrices. Let me explain what this is really briefly. This is a useful construct that will probably come up a little bit more tomorrow. This is called map. What map does is you can take any function, say f, and suppose you have a list. Map will just take this function and it will apply it to all the elements of the list. You don't have to count them up. You don't have to make any dummy variables. You don't have to do any iteration, blah, blah, blah. It just takes the function you want and it maps it across all these elements. So what I'm doing here, this is a shorthand. So map f on, say, x is the same as f/at x. It's the way to think about this. Kind of don't like using there. X kind of implies a one-dimensional thing in this sort of writing typically. So these things are the same. And so what's happening here, if we kind of go through, is we have this matrix, right? And this matrix, and this matrix, and this matrix. And I'm just taking matrix form and I'm applying it to each of those things in turn is the idea. If I use matrix form without map here, I just use matrix form on the entire thing. The structure isn't quite what we'd expect because we think about this as a matrix of matrices. But then if we go down one level, we can no longer think about it as that. And we might think about it as a list of matrices or a matrix of lists. It becomes a little bit arbitrary. There are functions you can use in order to access the parts of a list as well. So one such function is last. Remember from above that my list was this. So last here will give us the last element of any particular element, which is a list. And there are a couple more. So take my list, right? One thing we could do is we could get the first element from my list, and you'll see that that is equivalent to my list 1, right? You can get the last element of my list. That's equivalent to my list -1. There are also two other ones that you might want to be interested in, which are rest and most. This will drop the first element of a list and give you the rest. So this would be 2 through the end. And then most does kind of the complement of this, where it gives you most of the list, but it drops the last. My list. And so this would be equivalent to my list 1. And then this would be up through the second to last entry. Now, these do come in handy, maybe more than you might imagine. Imagine you have some data set. We have I think these ones are all nicely formatted, unfortunately, for us in this case. So suppose I have this thing imported from the web. We can see here that it has some headers, right? The first entries are these, and these. We can kind of look at and this has some empty, it has an empty row at the bottom. But the point really is that it's got a list of headers here. And if we wanted to do, say, some analysis on the actual data in this little CSV data set, we could just use rest on I didn't save this data as anything, but we could do rest on this. And you can see that we've dropped the headers. And then we'd also want to get rid of the missing elements here, which, to be fair, we could do with most because they just happen to be the last row here. If you go to this data file on this website, you'll just notice that there's a blank row at the end. But there, with most and rest, we could get the actual data that we're interested in plotting. Just to note, there are also some named mathematical symbols, for example. There are some named mathematical constants here. These can also just exist in lists just fine. And these are just some examples of built-in functions acting on these inputs here.